Thank you. I'm Idan. I'm a PhD student from the Department of Biomedical Engineering in Tel Aviv. And I'm going to talk today about some methods we developed in our lab to detect cancer at its early stages using antibody conjugated magnetic nanoparticles. So basically, we're using super paramagnetic nanoparticles. What are these super paramagnetic materials? If you take ferromagnetic materials, you can see it is composed of many isolated magnetic domains. Each has its own magnetic moment. If I take just one tiny small piece out of the ferromagnetic material, I get a single magnetic domain, and that's what we call a super paramagnetic nanoparticle. So a super paramagnetic nanoparticle won't have the hysteresis curve like a ferromagnetic matter has, just the saturation curve. Okay, so these magnetic nanoparticles, so MNPs for short, are made of iron oxide core, which is covered with many types of biocompatible coatings, usually dextran or other materials that allows it to stay inside the body for long without triggering the immune system. These particles are small enough to diffuse through the blood vessel into the tissue and interact with the cells inside the tissue. Now, if we conjugate these nanoparticles with different antibodies like HER2, we can make them to accumulate at tumor site, because tumors sometimes have antigens which are specific to this type of tumor. So if we coat our nanoparticle with specific antibodies that fits a specific type of tumor, we can make our nanoparticles accumulate at tumor sites. One nice thing about these nanoparticles is that we can remotely deliver heat to them. If we apply an external oscillating magnetic field, we make these particles oscillate together with the external field, and they dissipate heat by two mechanisms. It's the Brownian relaxation and Néel relaxation. The Brownian relaxation means that the entire particle just rotates with the external field, thus generates heat, and the Néel mode is the same, but only the magnetic moment of the particle moves. And as you can see here, we took a machine for welding pipes, an industrial machine that it has a coil and generates magnetic field. We put a vial of magnetic nanoparticles at the center of the field, and we took pictures with the thermal camera. You see, in the beginning, you see only the coil that heats up because of the current. And after a few seconds, you see the nanoparticles also heat due to the magnetic field. So we devised a thermomagnetic image and treat method, which goes something like that. At the first stage, we inject the person with a serum that contains these magnetic nanoparticles. These nanoparticles are injected to the bloodstream. They circulate inside the body. If they reach a tumor, they accumulate on the tumor. If they are not reach any tumor, they just evacuate it to the urine. They have a non-metabolic pathway. Then after a few hours, we apply some oscillating magnetic field. Sorry. If there are some accumulation of nanoparticles, they will start to heat. They will generate heat that will dissipate through the tissues and will reach the skin surface. On the skin surface, we can use IR camera to observe the temperature pattern that develops. And we can detect whether there's a tumor or not, and if so, what is the location of the tumor. Furthermore, once a tumor was located, we can increase the field strength and treat the tumor. We can specifically hit the tumor up to a point that is killed, or at least we disrupt the biological processes in there, and in the same time use the IR camera as a feedback mechanism. So to see if this whole concept is possible, we first started by developing a mathematical analytical model. We assumed the tumor is a point source because we want to detect these tumors early. We assumed they are very small. And basically what we did, we solved the heat equation with some modification. It calls the bioheat equation. It's the heat equation which also includes heat generated due to the nanoparticles, heat generated due to metabolism, and evacuation of heat through blood perfusion. Okay, so one thing that we saw pretty quick, it was that detecting a tumor, if you don't assume any noise, it's very easy. You just see a nice Gaussian pattern after a while on the skin surface above the tumor location. But if you take into account the noise, like the thermal noise of the camera, you just don't see anything anymore, because this pattern is very, very small compared to the noise we have in measurement. So in order to overcome this, we developed some some signal processing model, which okay, let's do it. Okay. Anyway, we use the model signal processing scheme algorithm to actually bright these hotspots. And we did it by the following method. First, we took some reference picture without applying any field, without heating. You can see here, this is a picture of an actual experiment. You don't see anything here, right? You don't see any Gaussian pattern or hotspot or anything. So we took this picture, we subtracted the reference picture from it. We took only the region of interest. And when you look only at the region of interest, we also did some special filtering. And then you can see the hotspot very nicely. Once you see a hotspot, you need to decide whether it's related to noise or to a tumor, and if it's related to a tumor, you want to know what's the depth of the tumor. So we did this by simply observing the development of the Gaussian pattern, the amplitude. We looked at amplitude over time. You see, this is time, this is amplitude, and the blue curve is what we get from one of our measurements, and we compared it to the simulation result we have. So you see, this is simulation result for 1 millimeter deep tumor, 2 millimeter deep tumor, 3 millimeter, and so on and so on. And as you can see, it fits quite well to 4, maybe 3.5 millimeter deep tumor. Yes.
What's the reference image you subtract?
Just I took an image before applying the field, before I do any heating. So this compensates for any ambient temperature gradient that I have in the lab and everything that comes from the surrounding and doesn't interest me. Okay, it's very easy to do. And here you can see that this came from an actual tumor phantom because it behaves just like the simulation predicts. But if it has some funky, weird behavior, I can relate it to noise. So this way I'm doing two things. One, I'm deciding whether it's tumor or not. And second, I decide what's the depth of the tumor. So to test this algorithm, we did a series of experiments. the first experiment, we wanted to be very controlled, very precise. So what we did, we put a controllable heat source inside ultrasound gel, which mimics the tissue thermal properties. And we also put a polymeric cover here on the top of it to simulate the skin thermal resistance. And we took pictures with the IR camera, of course. And this way, we can control exactly the location of the heat source, and we know how much heat is dissipated because we control the source. And we can train the algorithm with this setup. The second setup, we wanted to be a more realistic setup. We used pork tissue, and we created a tumor phantom, which was made of agar gel with these nanoparticles we had. We put it inside the tissue carefully. We heat it with the magnetic induction device and took picture with the IR camera. So what we got was this. First, what I'm showing is, here you see the peak value of temperature difference, of the height of the Gaussian, for 140 measurement, 70 measurement for no tumor at all, and 70 measurement for 13 millimeter deep tumor phantom with 400 milliwatt of heat dissipated. And you can see that if we fit the two Gaussians to the measurement, there's a very good difference. It's very easy to discriminate between the two. Just put some amplitude threshold or something here. So, and this is for what we called worst case scenario, okay? For the deepest tumor we planned on detecting versus noise. So if we can do it in 13 millimeters, we can obviously do it in 5 or any sharp map. Deep beneath the tissue surface. Beneath the skin.
But can you heat it by 400?
Yes. We can by... It's not a question of can we, it's a question of how do you stand with regulations, and I can always apply greater fields, but yes, of course. We took some previous works which investigated the concentration of nanoparticles that you can achieve in a tumor, and the numbers are around 10 milligram per milliliter of tumor. Okay, so we use the same amount, and this is achievable. Okay, this 400 milliwatt is very much achievable. Okay, it's not a problem. Also, we did a series of blind tests, and we tested sensitivity and specificity. Okay, what we can see here, we tested it for a different amount of heat that we deliver to the tumor phantom, and what you can see here is that it's virtually 100% until some threshold, and then it drops down to nearly zero. So it means that for every amount of heat that we inject, that we deliver to the tumor, there's a finite threshold, finite depth that we can detect. Any tumor that is deeper than that, we won't be able to see it. We won't be able to discriminate between it and the noise. We did it with very high specificity. Also, we tested, yes?
What is specificity?
Okay, you have two you usually have two or more measurement of your test. The first one is sensitivity, is the probability given a sick patient, is the probability of diagnosing it is sick, and specificity is given a healthy patient, the probability of detecting it is healthy. It's not a problem to construct a system that will have 100%.
How do you mimic that?
You do experiments on both with tumor and without tumor. You apply the same algorithm. This is a blinded test.
In animals or?
No. This is all I showed you on pork tissue. We took a slab of pork tissue, and we did. This is, of course, not a clinical number. Yes, it's still laboratory experiments. Yes.
So I guess you could also have a non-specific binding of your nanoparticles inside the
Yes.
right? So that could first introduce some sort of Fourier signal, right? And the other is that you can start worrying about the effect of heating in the non-specific
Yes.
binding.
These particles, basically what we used, they are called the Feridex. This is the commercial name. And they have what the clinician call clearance. It's the amount of time that takes 99 point something % of these particles to evacuate from the body. So after 24 hours, they have clearance of 24 hours. After 24 hours, every particle will be evacuated from the body, whether it's attached to a tumor or not. After a few hours, mostly what we will see, it's mostly those that accumulate on tumor sites. There will be a few in here or there, but they won't generate enough heat for you to see. Also, what is not mimicked here, and it's important that the body has temperature regulation. So if you start to rise the temperature somewhere and it's not a considerable heat source, the body will just regulate temperature and you won't see it. Anyway, then the next thing we wanted to test was our estimation algorithm. We wanted to see how good we estimate the depth of the tumor. And again, for 400 milliwatts of heating, which is the maximum performance that we can achieve, we see that up to 13 millimeters we can estimate the depth quite good. Standard deviation of 0.2 millimeter. However, we had some problem with these measurements. It was timing issues. If I want to detect the tumor and I look on the temporal development of this hotspot pattern, I need to wait long enough to see that this is the pattern behaves, or this behaves like my simulations. And the deeper the tumor is, the longer it takes for this pattern to develop. So for a 2 millimeter depth tumor, in only 7 seconds I can tell you whether it's a tumor or noise. For a 5 millimeter deep tumor, it takes 40 seconds and it rises exponentially. So this is a problem if I want to detect in real situation and I need to scan throughout the entire body or at least throughout the entire organ, this might pose a problem. So at this point we started to thinking about other ways to detect the thermomagnetic system was nice. We've seen that it's worked, it has potential, but we started to think about other ways to detect our tumor. So the first thing we noticed is that the heat was proportional to the intensity of the field, the amplitude square of the magnetic field. But if we apply field gradient, if we apply a field that changes over space, we can also apply force. We can also pull these nanoparticles toward our coil or solenoid. And what we thought about it is if we can use 2 coils above and below the tissue, and we can make these nanoparticles vibrate coherently, maybe we can create an acoustic dipole. And if we create an acoustic dipole, an acoustic field, acoustic waves will be propagating from the tumor onward into the skin surface, and we can solve the acoustic equation and estimate the shape of these waves and detect the tumor acoustically. So previously, the first system was Thermomagnetic detection. Now we want to do Magneto-acoustic detection. Again, we inject these nanoparticles into the body. Again, they will accumulate in tumor sites. And again, we will apply magnetic field, but this time we will apply a field gradient. An oscillating field gradient. And this will generate an acoustic dipole, which can be picked by an acoustic probe. So again, we started modeling the entire scenario. We actually wrote 6 or 7 submodels, each designed to describe the different components of the system. There was an inductance model, which allows us to predict the inductance of various solenoids. There was a model for the driving electric circuit, which needs to drive these two solenoids, as you can see here, above and below the tissue. We had a model for predicting the magnetic field that will be generated, the magnetic force that will be generated as a consequence, and also the tissue itself applies force on the tumor. If you start to move something inside the tissue applies both elastic and drag force. So we modeled this as well, and we did the acoustic modeling to estimate the shape of the acoustic wave. And finally, we also modeled the acoustic sensor itself, including the noise that it will be. Yes, there are mechanical resonances at very low frequencies, about 1 kilohertz or even lower. But we didn't want to work near the mechanical resonance. We preferred to work above, in the ultrasonic regime. We worked at 30 or 40 kilohertz. It's much more quiet. You don't hear all the noises from the lab. And it's if you work at very low frequencies, you actually destroy your resolution because the wavelength is very, very long. So we prefer to work at higher frequencies, but
For the heating itself?
For the heating, we worked at about 400 kilohertz. As you saw, there was a term there that was relative to the frequency. So we would rather work with higher frequencies. Also, the particles themselves have magnetic susceptibility, which is a function of frequency itself. So it's better to work at higher frequencies. For the acoustic measurements, it's better to work, I don't know, some medium-low frequencies, is why I call them, a few tens of kilohertz. And the first thing we did with this model, we designed and optimized solenoids. We wanted to manufacture 2 solenoids which will allow us to apply maximal force on the tumor. So there's some trade-off here, because if you do a lot of windings, you think you might create a greater field, but you can push less current into the solenoid. So there's some sort of optimization problem here. And we designed optimal solenoids, optimal in the sense that they will apply maximum force on a 3 centimeter deep tumor. Some of the simulation results, we look at the tumor displacement, velocity, and acceleration. We see that the displacement is very, very, very small. It's in the order of nanometers. And it makes perfect sense because you can't move things a lot inside the tissue without the tissue to react and restore them back to place. There are elastic forces. So movements of 20 nanometers or so are very sensible, are fine. Also, we look at the velocity. We see the velocity is on the order of few micrometers per second. This is also important. Why? At some point, we thought about detecting the movement of these nanoparticles with Doppler ultrasound. And the Doppler shift is, of course, related to the velocity. We see the velocity is very small, so it will be hard to get a good Doppler shift. But we see the acceleration is actually okay. It's a few centimeters per second square, which is measurable. And as we saw earlier, the acoustic dipole strength is directly proportional to the acceleration. So it's so we rather measure something which is proportional to the acceleration and not the velocity or displacement, of course. And if we look at the simulated pressure wave picked by the acoustic sensor, we see a series of inverted spikes, which corresponds to the pushing and pulling of the nanoparticles. And we see that the deeper the tumor is, obviously the amplitude shrinks, and also the signal is smeared and delayed because it takes much more time for the more time for the acoustic signal to reach the sensor. And we wanted to validate this model as well by experiments. We did a series of experiments. I'm going to show you only two. The first one, we wanted to measure how much force can we actually apply. And this force is on the order of micronewtons, so it's a bit difficult, a bit tricky to measure. What we did, we took a laboratory weight, a very precision weight. We put some plastic stand to distance the solenoid, the nanoparticles from the weight itself. We put here a Eppendorf tube with a Feridex solution, which is a solution of diamagnetic material called saline, which is compatible with human blood. You can inject it into the blood, saline, with magnetic nanoparticles inside it in a concentration which mimics real tumor. Okay, with the concentration here was, I think, 11.2 milligram per milliliter, which is almost the same as what we got in what we saw in animal experiments. And we put a solenoid above the Eppendorf weight, and we applied the field, and we adjusted the solenoid height. And what we got was this. These are the measurements, and in blue you can see our model, and you can see the behavior is quite the same, except from when we are very close to the solenoid. This can be expected since the solenoid in simulation is perfect and completely round, and in reality we have all these quirks, so it's okay for when you're close to the solenoids to see all this non-idealness. In the second experiment I'm going to show you, we wanted to actually see what the acoustic signal we get from a tumor phantom. So what we did, we built an acoustic bath. The acoustic bath simulates the tissue in the sense that it actually absorbs the outgoing waves, so they won't bounce from walls. When I speak to you here, the acoustic wave bounces from the walls, and we have revibration. It goes back and forth. We wanted to cancel this revibration because in real life the acoustic wave just propagates outside and bounces off. So we built this acoustic bath, We placed our solenoids. We placed a tumor phantom made of agar gel with nanoparticles and acoustic sensor. And what we got was basically this, which looks much like our excitation noise. It's an electromagnetic noise. We excite the solenoids with square wave, and as you can see, what you measure in the sensor is also a square wave. But if you do the signal processing and subtract the square wave excitation from this pattern, what you get is this, which looks very much like our model of, if you remember, the series of inverted spikes corresponding to the pushing and pulling of the nanoparticles. So we did this, and then we compared it to a situation without the tumor. So as you can see here, it's our in red. It's our the simulation, the model, versus true measurement, and you see it correlates very nicely. And here we took a situation without a tumor. We did the same signal processing algorithm, the same subtraction, everything. Oh, sorry. And you see just residual noise. It doesn't look like our model at all. So it's very, very simple to see whether there's a tumor present or not. You just need to correlate with the model and threshold the correlation at some point. This was done for a 3.5 centimeter deep tumor, which is quite nice. It's very deep. So to conclude, we showed the thermomagnetic detection, demonstrated theoretically and experimentally using tissue phantoms. We saw very high sensitivity and specificity, a depth of 12 or 13 millimeters, also very high accuracy. The problem was with measurement times. So we did a magneto-acoustic detection. Also, we demonstrated theoretically and experimentally. This time we used agar gel phantom, and we demonstrated detection of a 5 millimeter wide, 3.5 centimeter deep tumor very fast, less than 1 millisecond. That's it. Any questions? Yes, we'll start with you.
Maybe by different classes of nanoparticles. So if I have 3 antibodies, each conjugated to different nanoparticles, I can activate them separately in the same tumor.
First, it depends on what scheme you're using, the thermal or magnetic scheme. We can, in principle, construct nanoparticles that will respond to different frequencies of the magnetic fields. So I can either excite one type or the other type. So I can pre-design them to be specific to some frequency. Okay. Ours were used responding to the 400 kilohertz frequency. That's it. Thank you. Yes.
I guess it's more of a comment than a question. Why all this effort to detect the presence of the MPs using techniques which seem like they're doomed to be difficult? In other words, they're all, both the techniques that you mentioned, you're fighting a losing battle with diffusion. Your signal is diffusing away. On the other hand, it would seem to me that these MPs should show up like searchlights in something like MRI or just X-ray imaging. It looks like you're standing on your head to do something that should be easy in a different technique. So what's the motivation? What's wrong with X-ray or MRI?
Okay, sure. Let's start with X-ray. X-ray is ionizing. If you want to do a screening test for large section of the population, you can't just send everybody to X-ray.
You're not going to inject nanoparticles to a large section of the population.
Why
either.
not? Why not? They are already approved by the FDA. They are already approved by Israel Ministry of Health. They don't have any. Up to now, there's no any research that shows they have any dangerous effects. They are much cheaper than doing MRI. You can't put the entire population through MRI. MRI is, I don't know, it's very expensive. It takes a lot of time. You need radiologists to decipher the image. This is automated, and this is also cheap. It's not very complex. All we used was acoustic sensor, which is very cheap. The machine we used to generate magnetic field was either a laboratory power source or industrial welding machine. These things are cheap. This technology is cheap. It can be done in the point of care. And when I say point of care, I mean it can be done in home, in medical centers, wherever your patient is. I can do it there. I don't need any special equipment. I don't need radiologists to decipher the image. Okay, this is actually much cheaper than.
It also detects tumors which are very big, right? And
No.
only very close to the surface. And what is the size that you can size the tumor that you can detect?
Okay. Obviously, the detection limit depends on depth. With both methods, we focused on tumors which are few millimeters in size, which is considered very, very small. It's in if you think about tumor staging, stage 1 is localized tumor, stage 2 it's spread in the entire organ, stage 3 is also sends metastasis to different organs. So we catch it in a very, very early state. Whether it's 5 millimeter or 7 millimeter clinically, it doesn't matter. But what we showed, we showed it for a 5 millimeter tumor. Okay? For example, in lungs, the doctors, tumors below 3 centimeters wide are not considered the tumors at all, and they will just tell you to come another.
5 centimeters from your skin.
I don't know. I think a lot. We actually we built one of the applications we thought about was for breast tumor detection to replace mammography. Mammography used a lot of radiation, and if you look on the volume of the tissue, which is 5 or so centimeters below the skin, it's most of the volume. As for lung cancer, I don't know. I didn't think about it, but I think 5 centimeters is quite deep. There's a lot of. Also, 5 centimeters not the detection limit. We only demonstrated that it works on 3.5 centimeters.
Let's ask it the other way around.
Okay.
I mean, as part of the detection, this is one part of the story. The second part of the story is the
treatment. Yes,
if you would have an X-ray or an MRI image that tells you exactly where the particles are, can you use this information in order to treat with the vibrations hitting the source? Because then, in terms of regulations, you also have an advantage because you are targeting a specific location.
Yeah. These nanoparticles are actually used today as MRI contrast agents. But, okay, first, as of today, no MRI, X-ray, any type of imaging is considered to detect a tumor. You have to do a biopsy. If you want, No, as of today, no test, no mammography, X-ray, ultrasound, every type of imaging. It's okay, but it only leads to another test and another test and another test, and in the end they do a biopsy. Okay, only a biopsy result is considered clinically sufficient to determine whether it's a tumor or not. If I knew the actual shape of the tumor through MRI or X-ray, it would help me much, because I don't care what the actual size. I know it's conjugated with nanoparticles, and I can hit them. I don't change anything in the field. I don't assume I know where the particles are. I just apply this field. The whole beauty of this system is that I don't need to know the exact shape, the exact location. I just apply a field, which the body doesn't see at all. Only the particles respond to it.
You don't have eddy current effect when you apply?
No, you don't have any eddy currents and no hysteresis losses because of the size of these tumors, of these nanoparticles.
No, I don't speak about the nanoparticles, being about eddy currents in the body, because you have everywhere fluid, so if you change the magnetic field, you will induce elevation of temperature, anywhere really.
No. Not at these frequencies. The body is also almost transparent in these frequencies. It's like you can, let's say, at a few hundred, you're below the microwave. If you will raise your frequency above a few hundred and you reach the microwave regime, then the tissue will start to absorb your RF radiation and will start to heat.
You never heard of radiothermy?
Hmm?
You never heard of radiothermy?
Radiothermy?
Radiotherapy.
Radiotherapy, but it's not at this.
Radiothermy. It's a treatment used by physiotherapists for heating muscles. It uses, I don't know, what frequency is radiothermy? It's 200
kilohertz.
Maybe we'll continue this discussion over the coffee break, because we're a little bit behind schedule, okay? So let's thank all the speakers again.